Welcome to clickmyproject.com. A trigger identification of defending reactive jammers in wireless sensor network. The security of wireless sensor network has attracted numerous attention due to its wide application in various monitoring systems and invulnerability toward sophisticated wireless attacks. Among these attacks, jamming attack where a jammer node disrupts the message delivery of its neighboring sensor nodes with interference signals has become the most critical threat to wireless sensor networks. We present an application layer real-time trigger identification service for reactive jamming in wireless sensor network, which promptly provides a list of triggering nodes using a light-weighted decentralized algorithm without introducing either new hardware devices nor significant message overhead at each sensor node. This service exhibits great potential to be developed as reactive jamming defending schemes as an excluding the set of triggering nodes from the routing paths. The reactive jammer will have to stay idle since transmission can be sensed. Even though the jammers move around and detect new sensor signal, the list of trigger nodes will be quickly updated, so are the routing tables. This is the flow of our project. Consists of models: network formation, attacker model, jamming range, jamming detection, and performance evaluation. In network formation, in this model we design the network that includes such as bound nodes, sensor nodes, and jamming nodes. The next block is attacker model. This is attacker model. We consider the basic attacker model. Conventional reactive jammers are defined as the malicious devices which keep idle until they sense any ongoing legitimate transmission and then emit jamming signals to disrupt the sensed signal instead of the whole channel, which means once the sensor transmission finishes, the jamming attacks will be stopped, called sleep period. The next one is jamming range. Similar to the sensor, jammers are equipped with omnidirectional antennas with uniform power strength of each direction. The jammed area can be regarded as the circle centered as the jamming node with radius r, where r is the assumed greater than the sensor's radius. For simulating a powerful and efficient jammer node, all the sensors within this range will be jammed during the jammer backup period. The next block is jammer detection. Each sensor periodically sends a status report message to the base station. However, once the jammers are activated by the message transmission, the base station will not receive these reports from some sensors. By comparing the ratio of the received reports to a predefined threshold, the base station can thus decide if a jamming attack is happening in the network. By using the number of acknowledgements received, affected nodes are find out. After the next model is trigger detection. The base station makes a short testing schedule message which will be broadcasted to all the bounded nodes. Bounded nodes keep broadcasting to all the victim nodes within the estimated jammed area for a period Q. All the victim nodes locally execute the testing procedure based on the message and a global uniform clock, identify themselves as a trigger or non-trigger. After the trigger node is detected, we can remove the jammer node and the trigger node. After identifying the jammer location and the trigger node, we hide the jammer node and the trigger node. The data transfer can take place through the remaining nodes. In performance evaluation, in this model we calculate the performance like packet delivery ratio, delay, and throughput. We calculate these three parameters in case of jammer and without jammers. Simulation research show that our proposed method performs better than the existing methods. Open the source code folder, run wireless WSN.m file. New window is appeared. Initially, network formation creates a number of nodes. Here I use 30 nodes for our simulation. After the jammer detection, that is jammer range and the jammer location. This is the jammer node. I consider two jammer nodes and the jammer range. Jamming range is the circle represents the jamming range. After that, I calculate the affected node within the jamming range. These are the green color shows the jamming affected nodes in the jammed area. After that, the seventh node is a trigger node. I display this seventh node is a trigger node and remove the jammer and the trigger node. Jammer node is removed and the trigger node is removed here. After that, I calculate the performance evaluations of packet delivery ratio, delay, and throughput. Figure 2 shows the number of nodes versus packet delivery ratio. without jammer, then packet delivery ratio is higher, low, and compared to with jammer is compared to exiting method, our algorithm performs better. Here is a throughput. In the case of present of jammer, the throughput is minimized. Without the jammer, the throughput is maximized. Here the delay is minimized in the case of without jammer. Delay is maximized in the case of jammer. From this I conclude that our proposed algorithm achieves better performance in the jammer location, detection of jammer location, and trigger node identification, and remove the trigger node and the jamming node, and achieves high packet delivery ratio, delay, and throughput. Thank you.